Hi, welcome back to our Honors Geometry playlist. On this video, we're going to do some coordinate proofs involving congruent triangles. So on this particular video, let's take a look at a proof that two triangles are congruent, given that GJ, ray GJ, bisects angle OGH. So this is a common stumbling point for many students. That's the angle that's being bisected up top, which means that the left half, which I would name OGJ, is congruent to the right half of HGJ. So you have to be very careful. Please read the directions and identify what in the world is being bisected if you see the word bisector. So step one would be my given step. I've got GJ bisects OGH. That's given. I've got GJ is congruent to GJ by the reflexive property. And from here, the proof looks pretty similar to what we've done in the past without coordinates. So what I need now is I need to figure out, again, what angles are congruent since it was bisected, and those angles, again, must be angle OGJ and angle HGJ up top. And that was by the definition of what it means to be an angle bisector. So now I have these parts of my triangle. What I want is to prove congruence. Now I could do another pair of sides with the distance formula, and I could do a third pair of sides with the distance formula, and I could get side, 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 but that feels like a lot of work, and I want to be lazy here. I want to be efficient. So I'm going to try to prove side angle side congruence, which means I need OG to be congruent to HG. So what I'm going to try to do is I'm going to try to prove that OG and HG are equal. I'm going to use the distance formula. So let me find my coordinates. O is 0, 0. So OG, if G is 3, 5, would be 5 minus 0 squared plus 3 minus 0 squared, which means that is the square root of 34. HG, H is 6, 0. So HG would be you could do 5 minus 0 squared and 3 minus 6 squared, and the order there really doesn't matter since addition is commutative, and you would end up with another square root of 34. So I've proven that those are equal by the distance formula. And now that I've got that down, I need to say that OG is congruent to HG by the definition of congruence. If they're equal, they're congruent. And now I have my first side, my angle pair, and my side. So I can say that these triangles are congruent. What is that? GJO and GJH, GJO and GJH must be congruent by side angle side. So the whole point of this is to take what you're given and use the distance formula when necessary to prove congruent triangles. So here's another example. I've got G is the midpoint of HF. GHJ is congruent to GFO. So my given step, or you know what, is there a better one? Let's do this one. I lied. I like this one better. So I want to prove that these triangles are congruent. There are no vertical angles. There's nothing bisected. So my first step would be my given step. I would list out all my coordinates. O is 0, 0. T is m comma k. U is m plus hk. And v is going to be h comma 0. So that's my given. Now that I've got that given, I want to prove congruence. Well, I can pretty easily go with OU is congruent to UO by the symmetric property. That shared side in the middle. And now I need two other sides. So I need to show that TO and UV are equal. So I'm going to find the distance of TO and the distance of UV. So let's find those. And all we're doing here is we are just substituting these values from T and O into my distance formula. So it would be k minus 0 squared, y2 minus y1 squared, and m minus 0 squared, x2 minus x1 squared, which is the square root of, if I simplify, k squared plus m squared. UV, similarly, just substitute in those values. I've got m plus h minus h squared plus k minus 0 squared. And when I simplify this, I get the h's would reduce, and I would end up with k squared plus m squared. And perhaps I should have rearranged this, right, where I get the same exact thing. So I've proven that those two sides are equal. That's good. TO and UV. Now I need to prove that TU and OV are equal. So TU would be m plus h minus h squared plus k minus 0 squared. And that would get me, the h's would reduce here, and I'm left with m squared plus k squared. And I would do the same thing for OV. I'm going to change back to gray just so you can see it a little bit better. And OV would be TU I'm sorry, I made a mistake. TU it's m plus h minus m. And that would be k minus k. My goodness. This is why you don't do things on live television here. So this is m plus h and m, and k minus k. All All right, when I'm setting up the TU and OV, what I'm going to do is TU, I've got m plus h minus m, where the m's would reduce, and then I get k minus k. And those would reduce, and you're left with just h squared. And then for OV, that's not what I wanted. For OV, I've got 0 minus 0, which doesn't do anything, and h minus 0, which would simplify to the square root of h squared. So what I've shown here is that I have one pair of congruent sides, two pairs of congruent sides. So here on my drawing, I've proven that one and two pairs of sides are congruent, which means that my next step, right, I could say that I have congruent sides, and then I have two congruent triangles by side, side, side. So there's some examples of our congruent triangles in coordinate proofs. Let me know what questions